In section 4.7, we want to synthesize all the things that we've been learning here in chapter 4 and to look at how can we make decisions and make predictions with linear models. So we're going to go back to working with our best fitting lines and using that data then to make decisions and predictions. So we want to make sure we know what a best fitting line is, what's linear regression, what is interpolation, what is extrapolation, and what is the zero of a function and what does that mean? So let's start off with the line that most closely follows the trend in the data is called the best fitting line. We talked about that in the last section. And the process of finding the best fitting line to model a set of data is called linear regression. So in a really basic and rudimentary way, when we select the 2 points, we put the line in, we select 2 points, and we write an equation based on the line, that's called linear regression. You can also do linear regression using a TI calculator by putting the input-output data into a table and then asking it to do it for you. And so it actually selects the line of best fit and will actually give you an equation. This is important. Using a line or its equation to approximate a value between two known values, right? That's the key thing. Between two known values is called linear interpolation. So when I've got data, right? Let's say I've got data, right? And then I create a line of best fit for my data. When I'm taking a look in here, right, in this range here, this is approximating a value between two known values. I have a known value there and a known value there. And in here, this is called interpolation. It's rather predictable. I'm looking between things that are known, and I'm trying to make decisions here. This is called interpolation. Now, if I look out here and I'm beyond, or out there and I'm beyond my known values, now what we're talking about is called extrapolation. Now I find that in working with this in the ways I'm most familiar with, extrapolation is done a little bit more than interpolation. Just because, again, I tend to think about business models a lot. And if I look at monthly sales for a period of time, I may want to predict what are my monthly sales going to be in the future. That's extrapolation. Okay, but if I was doing other research, maybe I'm looking at other things, I may want to be doing interpolation. Just because I happen to think of extrapolation more doesn't mean it's more frequently used. So if I want to use interpolation, I have a data model here that's going to show me the CD singles that are shipped, and they want me to make a scatter plot of the data and then make an equation and then approximate for 1994 in here. Okay? So if we take a look, and I'm just going to do this in a very rudimentary way. So let's go 1, 2, 3, 4, 5, 6, 7. Okay? So this is 97. So this is 90, 1, 2, 3. This is 93. And then we have 4, 5. That's 95. And then we have 6 and we have 7. And then we've got these numbers. And let's say we got 10, 20, 30, 40, 50, 60, 70. CDs. So in 93, we're talking about 7.8, right? So right about here. And in 95, we were at 22, right about there. And then we're at 96, we're at 1, 2, 3, 4, 43. And at 97, we're at 67, 10, 20, 30, 40, 50, 60, right? So something like that. And this data does look, it does look like it's got a linear correlation. It looks like I could probably do a line of best fit like that. But what's most closely related to what was happening in 1994. I'm really going to look in between the points of 93 and 95. Okay, you'll see that it could be argued that this is more of an exponential growth model, right? I might be able to use this line, I might not. But I'm just going to use 93 and 95 as the data. So I think that's going to give me my best line of fit for that area. So I'm going to find my slope. 22 minus 7.8. Right, that's a big difference in just the 2 years. See, and you'll notice the difference here is about, a little less than 15, whereas it's more than 20 here, and then it's more than 20 here. I'm not so sure, right? So, and you see I've got this upside down. I'm sorry, so I'm going to switch this. My mistake. It's going to be over 2. And this is going to be 15.8. No. It's going to be 14.2. Okay, divided by 2, so that's really 7.1. If I want to write the equation, I'm going to take one of these points. I'm going to take the one with whole numbers. So I'm going to take y minus 22, and I'm going to make these, right, 3, 5, 6, 7 instead, to make this a little easier to calculate. Equals 7.1 times x minus 22. Okay, so I'm going to go ahead and use a calculator to do 22 times 7.1 is 156.2. So I'll have 7.1x minus 156.2. And then we're going to add 22 to either side. Right, that's going to be minus 134.2. Now, if we want to go ahead and evaluate this for 1994, y is equal to 7.1 times 4. Oh, my mistake. Start over. Wow. So I'm going to want to calculate the slope, and I'm going to work between 93 and 95. So my y values are going to be 22 minus 7.8 over 5 minus 3. And what I'm doing is I'm using years since 1990. It makes the numbers a lot easier to work with. So 22 minus 7.8 is 14.2. And this is 2, so that's 7.1. If I want to write my equation, I can use y minus 22 is equal to 7.1 times x minus 5. Okay, so y minus 22 is equal to 7.1x minus 5 times 7.1 is 35.5. And when I add 22 to either side, y is equal to 7.1x minus 13.5. Okay, now if I want to find for 1994, y is equal to 7.1 times 4 minus 13.5. Okay, and this is going to be 28.4 minus 13.5, which will be 0.9. 14.9 is what we would have expected the sales to have been approximately in 1994. Okay, and that's the interpolation of working in this data set, right? I didn't have to do it this way. I chose to work with these points. I could have picked these 2 points to be the line of best fit to make the equation. I could have picked a point that wasn't on the line. But I chose to use those because I felt they best modeled the situation. So if we go back and let's look at that same equation, what do we think would happen for the number of singles shipped in 1998 and 2000? So if we look at 1998 and 2000, right, those are going to be 8 and 10 years since that, but we're still going to use the same equation. So let's use this equation. And I wrote it awfully crooked, but we're going to go ahead and use this equation. In fact, let me rotate it so it's not so. There we go. There, it's a little flatter now. That's better. Okay, so if I want to work in A, I'm going to plug in the values 8 and 10 into my equation. So y would be equal to 7.1 times 8 minus 13.5. So this is going to be 56 and 6.4, that's 62.4, minus 13.5. 0.9, and then this is going to be 11 minus that is 8, and 5 minus 1 is 4. So 48.9 for 1998. And for the year 2000, it's 7.8 times 10 minus 13.5, which is 78 minus 13.5, which is going to be 0.5. 7 minus 3 is 4, 7 minus 1 is 6, so 64.5. Okay, and in 1998 there are actually 56 million shipped, and in 2000 there were 34 million shipped. Describe the accuracy of the extrapolations. Well, they're not very accurate. This one's pretty accurate. It's pretty close. Right, it's maybe a little shy because I made my line probably a little too flat based on the points that I picked. Okay, but this one, 34 million CDs in 2000. Why? What happened? Why didn't this happen? We should have sold 64.5 million of these things, and instead we sold half that, right? A little more than half that. What happened? Well, digital music happened. File sharing happened. So people stopped buying their music on CDs and they started downloading it. iTunes happened. These are all the things that happened. And the technology changed. So extrapolation is dangerous. Interpolation is realistic. But extrapolation is a guess. It's an educated guess. But there are a lot of outside forces that can happen to change the accuracy of what happened. Okay, if we take a look here, number of participants in youth softball during 97 to 2001. Predict the year in which the number of youth softball participants reaches 1.2 million. Well, this is going to be extrapolation because it's going to be, oh no, it's declining. It's going to be extrapolation because it's going to be beyond our known values. All right, again, let's work from years since 1990. So we're going to use 7, 8, 9, 10, and 11. It's a lot easier to work with those numbers. They work better with these numbers when we start doing our line of best fit. And what I'm going to do is I'm just going to go ahead, I'm not going to draw the scatter plot. I'm just going to assume that I can use this point and this point for the most accurate. That's not totally valid, but I'm going to do it to save us time. Okay, so if I look at my slope, it's 11 minus 7. Sorry, I keep doing this upside down. I'm not sure why. It's 1.355 minus 1.44 over 11 minus 7. So it's going to be over 4. And it's going to be a negative number. Let me go ahead and use a calculator for that. So I'm going to do 1.355 minus 1.44. And it's negative 0.085. And then let's divide that by 4 so we end up with a decimal. 0.02125, negative. So I get negative 0.02125 as my slope. And now if I go ahead and write an equation, okay, this is going to be a little different than the things we've done before. I can pick one of these points. I'm just going to pick the first point, right? So I know that y minus 1.44 is equal to negative 0.02125 times x minus 7. Okay, so let's go back to our calculator. And let's take that number and multiply it times 7. So I'm going to get 0.14875. .14875, and I'm going to get negative 0.02125x y minus 1.44. If I add 1.44 to either side, I need to change this sign, and I'm going to add 1.44. So I got 1.58875. And over here I have negative 0.02125x and y equals that. So what they'd like to know is what's the year, right? So this is my equation. What's the year in which the number of participants is 1.2 million? So that's going to go in for the y. Right? So 1.2 million will equal negative 0.02125 times x number of years we don't know, plus 1.58875. So let's go back to that calculator. And let's find the difference between that and 1.2. 0.38875. Negative 0.38875 is equal to negative 0.02125x. So going back to my calculator, so I've got 0.38875 divided by negative 0.38875 divided by 0.02125 negative equals 18.29. Okay, 18.29 is equal to x. So that's going to be about 18 years from 1990. So that means we're looking at approximately midway through the year in 2008. right? It's going to be between 2008 and 2009. 0.29, that's a third of a year, right? So that's about 4 months. So probably somewhere around in April of 2008. Okay. Another example, or a little more information talking about the zero of a function. A zero of a function is a value of x for which the output y is 0. It's also the x-intercept, right? Anytime my y value is equal to 0, I'm going to hit the x-axis, so it's the x-intercept. And when we're talking about solutions of quadratic functions or cubic functions, we're always talking about x-intercepts, and we also call them zeros. Okay, so what I do to find a zero is I set the equation to be equal to 0, and then I solve for x. Okay, because I'm looking for the value of x when y was equal to 0. Okay, and that will always be the x-intercept. So let's take a look at this. Where's the zero of the function, and what would that mean? So let's talk about that. So let's take our crazy equation, right? And I want to find out what happens when this equals 0. So if 0 is equal to negative 0.02125x plus 1.58875, if I subtract from either side, I'll have 1.58875, and I'm going to divide, right, that would be negative. I'm going to divide by negative 0.02125, and that's going to equal x. Now I know when I divide a negative by negative, it's going to be positive, so I can forget about that now. Right, and if I go back to my calculator and I take 1.58875 divided by 0.02125 equals 74.76. Right, so 74.76. And what does that mean? Well, the zero of the function, remember what this was looking at. This was the number of people who participate in youth softball. Right? The zero of the function would be, in what year does nobody do this anymore? In what year has youth softball ceased to exist? Right? And this is the year since 1990. Right? 74, 76. So we're talking about 0.76. So midway, 3/4 of the way through the year, in the year 2064, if the trend continues as it has, no one will be playing softball anymore. Okay, so that's taking and using lines of best fit, doing interpolation and extrapolation, and trying to make predictions based on what your data and your models, algebraic models say.